We just learned in the previous video the set of piecewise continuous functions, PWC, on an interval AB. Right, and these are functions f and g. What I like to do now is I would like to get a vector space structure on PWC. In a sense, this is really just doing linear algebra. So I want to do linear algebra things with this vector space, introducing bases, introducing an inner product, and so on and so on. So to do this, let me just review a little bit of linear algebra. Now this is all stuff you should have seen in previous classes. I just review it relatively quickly. I skip the details. The details are in the textbook, and so you can look it up anytime you want. But here I just mention the essentials. So for example, if we take the Euclidean space R3, then we can have basis functions given by I, which is 1, 0, 0, j, which is 0, 1, 0, and k, which is 0, 0, 1. To give you already a taste of what's coming, the I will be something like sine of pi x divided by L. The j will maybe be something like sine of 2 pi x divided by L. The k could then be sine of 3 pi x divided by L. But of course you will not stop, right? In this sine series thing, you can then get 4 pi x over L, 5, 6, 7, etc. This goes to infinity. Okay, let's come back to linear algebra. So here we can then define a basis. The basis of R3 would be these three vectors I, j, k, or some people call them E1, E2, E3. And then each vector V you can write in components A1, A2, A3, which means it is A1, E1, A2, E2, and A3, E3. And similar for another vector W, which I have components B1, B2, B3. And then I can have a dot product of two vectors. And the dot product is just the product of A1 times B1 and A2 times B2 and A2 times A3 times B3, so as given right here. You should be rather familiar with all of this. Okay. Let's continue right here where we talk about the norm. So each vector can have a norm, and the norm corresponds to the length of this vector. And it is defined, the norm is defined to be the square root of v times v. Okay, so this is also then the square root of a1 square plus a2 square plus a3 square. And later we will define the norm of sine functions and cosine functions and that kind of stuff. Oh yeah, here's this formula which I just wrote down already. And now we generalize this definition. So what we had as a dot product now we call to be an inner product. And an inner product of a vector space is a pairing UV which has the properties of the dot product. Meaning, if I multiply u with u itself, it's always larger or equal 0. If I multiply u with itself and get 0 out of it, then u has to be 0. It is symmetric, so if I multiply u with v, that's the same as multiplying v with u. And it's linear, so if I multiply u to v plus w, I get uv plus uw. And then if I multiply by lambda one of the functions, then the lambda comes out of the inner product. Okay, so in Rn, our inner product u and v would be the dot product, as we have seen. But now what is it for PWC? So now we really want to go to our function space, piecewise continuous. And the dot product becomes the integral. The inner product will be the integral. So now we have two functions. F and g are two functions. And we integrate f with g. And then we allow another function w sitting here, which is called the weight, a weight function. Okay, so if the weight is equal to 1, for example, so if w would be just equal to 1, then we have the inner product f and g would be the integral from a to b f of x, g of x dx. Okay? So this is a formula you should try to remember. Now for the function space PWC, we use an inner product which is actually equal to the integral of the two functions.